if you're speaking, and we will kick things off. A couple of housekeeping notes. If you have any questions, please feel free to put those in the Q&A or the chat. The Q&A allows us to manage it, but we are looking at both of those. We'll also open it up at the end of the presentation for some open dialogue and get a discussion going as well. If you want to raise your hand, we can call on you that way as well. So without further ado, I want to introduce our team, our speakers. Our speaker today is Kenneth Yu. Kenneth is a hydroinformatics engineer with Opti. He provides the subject matter expert for floodplain analysis, water quality modeling, regulatory compliance, as well as doing our optimization projects. So he's super smart with a Master of Engineering from MIT. So we're really honored to have him with us today as he shares the design steps for our CMAC solutions. Also today with us is Rosa Santillan. If you were at our last webinar, you got to meet her. She is our project manager, where she develops and implements these solutions and works very closely with our partners and customers and making sure that each of these implementations go as smoothly as possible. So thank you, Rosa, for joining us again today. Last but not least is Victor Hlas. He is our Chief Revenue Officer and is responsible for promoting the solution and developing the solution and driving the industry. So we're looking forward to his insights as well as we get into the discussion later. Without further ado, I'm going to pass it over to Kenneth.
Thank you, Jennifer. Welcome again, everyone. Welcome to our Opti Design Partner Support Series webinar number 2. So last time Rosa covered feasibility analysis and some action items that we consider at the planning phase. So this time we'll talk about what happens behind the scenes when we selected a site and goes on to solution design. I'm going to do a quick recap here. So CMAC stands for Continuous Monitoring and Adaptive Control. That's Opti's main product. Comparing to traditional stormwater solutions focus on passive design structure. So a pond or an underground storage facility may be designed to capture up to a certain design storm, and that's it. There's an invert elevation, there's an overflow elevation, and once the precipitation volume goes over a certain amount, and an overflow event will occur, and no additional storage can be provided based on a passive design. Whereas in CMAC design products provided by Opti, we are able to look ahead into a weather forecast and make different decisions based on different goals and objectives at different sites and try to maximize the utilization of available infrastructure, or we can minimize the storage needed or the volume design needed for new designs. So what goes on to make it work, make this continuous monitoring and adaptive control work? There are 2 main portions of our product. There's the software side, there's the hardware side. Today, we're going to focus more on the software side. And within the software portion, we have 3 main components. Everything starts with precipitation weather forecast. Without the forecast, we cannot make any educated decisions. Our adaptive control logic wouldn't work. And at the same time, with that forecast information and all the infrastructure, sensors, all the data available from our customers' sites, all that data is available near real time on a cloud-hosted web-based O&M portal that is all our clients and customers can access anytime on their phone, on their laptop. And there's a portal they can look at the performance of the site near real time. One of the unique implementation that Opti can provide is to integrate third-party APIs, such as SCADA integration. We can talk to existing SCADA infrastructure, and we don't have to install any sensors. Like all that data and information can be captured and communicated between Opti cloud platform, Opti control panels, and the SCADA system. And all of that is connected to the hardware components installed on-site and on the cloud. Here at Opti, we provide three promises. First thing first, like everyone thinks about the economic savings. Our products can provide significant savings compared to more costly passive design or retrofits. To expand existing storage, which may not be feasible for urban environments when real estate space is highly limited, and we want to maximize the utilization of existing storage. At the same time, because we're always looking at data available, the performance of the site, and we can look at what changes are going on in climate conditions, which make existing infrastructure more resilient, and we can be adaptive and make changes as we see performance and goals and objectives evolve over time. And all of that because of the accessibility and data availability on the cloud platform, on the tablet, on the phone, on the laptop. It provides improved safety and compliance for all our customers. Like they want to know about the site, it's just a couple clicks away. Here, I'm going to show the life cycle of a typical CMAC project again. Rosa went through this in detail last time. Rosa talked about the feasibility assessment. Today, we're going to focus more on solution design. And after solution design, we have implementation, commissioning, and also after implementation, we also have a phase called optimization, where we look at more fine tunes of the system based on data collected over a certain period of time. So that's the feasibility assessment is the planning phase. And now today we're talking about the design and permitting, more regulatory related, and we're going through these 4 steps: software configuration, H&H modeling, certified hardware, and regulatory. Again, these are the 4 main steps for any software configuration for a chosen site to implement an Opti CMAC project. First step is to identify any stormwater challenges, to set our objectives. And then based on those objectives, we will work with the customer and also our product team to make a decision on what relevant behaviors, control logic that we want to implement. And after we chose the behaviors and the control logic, there are some site case-by-case key parameters that we need to establish and or refine. This could be anything hydrology related, such as watershed area, tributary area, runoff coefficient, and other more operational protocols related parameters. And then after all of this is determined, we'll plug that into our in-house H&H model. H&H stands for hydrologic and hydraulic model, and then we will simulate these behaviors with the established parameters to see if we are getting the expected results from the Opti product. Zooming into the challenges we usually face, if we have a very simple site, our customer only want to know more about the performance of an existing site. We don't need to do any control logic. We can just implement the monitoring system and provide any reporting, any data collection that is required to meet any compliance goals and O&M requests. That's just the starting point. Once we have the monitoring system, if we apply any control logic, we can help to solve any combination of these challenges that are commonly faced in stormwater communities, such as flood mitigation on coastal areas where there's urban, highly densely developed areas. There's not much space for development. We need to time our release and storage in a better way such that we can reserve more conveyance capacity. At the same time, maybe you have a cistern project where you want to keep as much water and for as long as a period of time as possible. And so to maximize reuse and capture for a water conservation system. And other examples could be water quality improvement by delaying that discharge of stored volume. We can increase residence time and promote settling. And we can also try to match pre-development flows. If we have a project, we need to meet a certain regulatory standard and minimize any flow rate requirements. With Opti products able to do that as well. So all of that is really related to these two ideas, these two concepts here. We're trying to shift that the peak flow rate by delaying that peak flow rate. Maybe we can delay it enough so that we are not releasing any water when it's still raining and when the downstream conveyance capacity is limited. Or in some cases, that's not possible. Like the site is designed way under capacity, and we can only try to flatten the curve, and we try to smooth the peaks. So we will release some water, but not all water at a certain time periods during wet weather, so that we can try to flatten that peak flow rate as much as possible. So we talked about some challenges. So how do we translate some of these objectives once we identified the challenges into CMAC behaviors? First, we look at what goes on in an existing site. Many of our projects are retrofits. So that means there's an existing outlet control structure, and we are retrofitting the site to install an Opti valve with the Opti control panel. And we first look at what the passive system design look like. In a passive design, the pond starts at a certain water elevation, and then once the runoff starts to come into the system, elevation goes up. And if that event produces more precipitation volume than what is available in the storage capacity, and overflow would occur until the rain event has passed. So, and it looks pretty much the same based on the rainfall distribution for all events under a passive system. And with Opti implementations, CMAC logic, we can drastically change how this hydrograph look like based on different behaviors. One of the more simple logic that we can implement is called pre-event drawdown. So imagine if we have a pond that has a wet pond that has a normal pool elevation start at this level. And by looking ahead from weather forecasts, we can see, say, there's a 1-inch event or half an inch event coming in the next 12 hours or 24 hours. Then we can control our Opti valve to release that stored water early on, like when we are still in dry weather, when downstream capacity is still abundant. Then we can draw down the pond to reserve for that forecasted runoff volume. Then when we transition into wet weather duration, we can close the valve so no water is discharged and the pond slowly filled back up until we reach that normal pool elevation that we started with. This can have many implementations for a lot of different objectives. It can help on CSO mitigation. It can help to restore conveyance capacity downstream of the ponds to mitigate any flooding. This can also help with a cistern water reuse project to keep as much water as long as possible. Another type of control logic is a post-event retention. So we still look at the CMAC control logic, still look at what goes on in the next 12, 24 hours based on weather forecast data. But we don't act to it until the rain event has passed. So for an example, there's a dry pond with a lower water elevation, normal pool, and once it receives runoff, the elevation starts increasing until the rain event has passed. And during the entire rain event, Opti control is going to trigger that Opti valve to close again, so no flow is discharged. And we are going to keep that valve closed for an extended period until the post-event detention period duration has met, and then we can start gradually release that water. So how does that help? Like, imagine if you have a water quality BMP implemented, we have a constructed wetland that you want to maximize the treatment capability for rain events, then you can increase the settling time by closing the valve for an extended period. And at the same time, we can also control how quickly the water is being discharged. So we can control how this drawdown curve look like as well. For some sites, there may be a maximum discharge rate limitation. So the Opti valve can maintain that discharge rate looking at a real-time elevation, looking at the real-time hydraulic head available based on the existing Opti valve dimension. Okay, so we talked about pre-event drawdown. We talked about post-event retention. One of the many benefits of the Opti products is that we can provide multi-objectives behavior. So imagine if you have a pond or water infrastructure, stormwater infrastructure that faces both downstream flooding problems and water quality treatment challenges. So we can reserve that storage volume to mitigate flooding by implementing pre-event drawdown, and also close the valve for an extended period after a rain event to increase residence time to promote settling. So this can all be implemented at the same site. And we can control all of these different settings. We can control where is that normal pool elevation at. It may not be the same elevation as the existing infrastructure because of improved performance provided by Opti products. We could be modifying the discharge curve again. We could be modifying how long we are storing that water for. Okay, so we covered how we translate the objectives into different CMAC behaviors. Then we go into a little bit more technical topics. We cover how we implement and establish some key parameters for the software configuration. Here we start with looking at hydrologic properties of a site. Again, for all the projects, everything starts with looking at precipitation forecasts. We have two main sources to gather our weather forecast data. The first one is National Weather Service, available to public, maintained by our government. Another source is a Boston-based tech company called Tomorrow.io. They use a proprietary technology that aims to provide a more accurate weather forecast with a smaller time step. Once we have this data, we translate this weather forecast into a runoff volume. But first, we need to decide, okay, what is a rain event? Do we consider a 0.01 inch precipitation a rain event? Do we consider a 4-hour duration to be one single rain event? What is the dry period in between that we establish an end to a rain event? So we need to decide on the threshold for probability and also the quantity. As you may know, National Weather Service and most weather forecast providers, they will estimate precipitation probability. Say for the next hour, there's a 50%, 60% chance for the precipitation to occur. So is there a threshold that we want to use? For many projects we start with a 60%. So we disregard any precipitation forecast that has a probability lower than 60%. And at the same time, there's also a quantity threshold. Maybe we want to disregard everything that has a volume under 0.05 inch. So that's a capability we can quantify as well. And both of these thresholds need to be met for our system to consider it as a qualified forecast. And once we have this qualified forecast, we will plug this data into our inflow estimate model. It's pretty simple. It's based on the rational method and takes in the watershed area and also the imperviousness. It could be a percent impervious cover, could be curve number based, but ultimately it translates to a runoff coefficient that gets estimated. And remember, all of these settings we can change once the site is implemented. It can be changed anytime after Opti CMAC is implemented, because as we gather more data, as we look at more data and optimize the site, we can make changes to improve the performance. Okay, that's all well and good. We have perfect weather forecasts all the time, right? At least we hope for that. But unfortunately, sometimes that may not be the case. Like we hear many stories in the Northeast region that we may see 6 inches of snow tomorrow, but it turns out to be rain. So at Opti, we always hope for the best, but at the same time, we always plan for the worst as well. We have different logic to allow the site to behave differently based on different conditions. In some cases, when the site it's designed to store most of the runoff volume that it sees, maybe it's okay to allow overflow, because we expect that most overflow events will not be discharging at a high discharge rate anyway, so it's okay. But for other sites, maybe it's undersized. That way, when for most rain events, it's going to cause overflow. How do we provide a better control logic then? We can minimize overflow by allowing some storage some stored volume in the pond to discharge downstream while maintaining the pond to stay under that overflow elevation. So that's the peak smoothing, flattening that I was talking about early on. There are also other operation settings that we consider to cover edge cases to improve reliability for our system. We look at what are some desirable elevations. Is there a maximum elevation that we don't want to go over, even if it means that elevation is below the overflow weir? Is there a minimum elevation that we want to maintain above for aesthetic reasons? Also, there is a fail-safe mode that we use for cases such as what if there's a power outage? We don't know what's going on. The on-site control hardware cannot communicate to the cloud server, so it doesn't know what to do. Maybe we will set it to behave like a passive system and open the valve fully so we can avoid to cause any local flooding around the site. There's also extreme event mode. What if there's a hurricane that we are seeing? We know that the site is not capable of capturing the entire runoff. What do we do? Maybe there is a default setting under extreme event mode that we want to consider. There are also other modes and configurations that we look at, but for this webinar, this is where we will stop. In the future, we'll also do a deep dive on some of these topics for anyone who is interested in the audience. So we covered a lot of the hydrologic properties. Now we can move on to the H&H model development. And the first thing we consider is the valve sizing. What's an appropriate size to retrofit or to put into a new system? Take this site as an example. On the graphic on the left, we are showing a drawdown curve for an 8-inch valve. The drawdown curve is showing us that to draw down the entire storage volume, it takes about 75, 80 hours. Is that okay? That may be a question that we need to discuss with our customer. For Massachusetts, as an example, where Opti is based in, Mass DEP mandates that for any BMP, any stored water has to be discharged and released within a 72-hour time period after the rain event has passed. So if that's the case, an 8-inch valve is not suitable for this type of implementation. Maybe we need to upsize it into a 12-inch valve instead. And at the same time, we also look at the stage discharge curve to make sure that we're staying under any flow rate requirement that we need to comply with. Everything I have mentioned just now, covering the valve sizing, can be done in a simple model in HydroCAD. But if we want to simulate Opti logic, we have an internal tool developed in association with EPA SWIM. This is a very simple high-level skeleton of an Opti control model. We have the tributary area, we have the Opti infrastructure, the storage facility. There's the Opti valve, the controlled outlet. There's the overflow weir. And then there are the downstream conditions. Okay, so do we just use the control rules within EPA SWIM to help simulate the Opti behaviors? Yes, to a certain extent. If we are only simulating a very basic behavior, we are only drawing down the pond and then close the valve for the entire rain event, maybe that's okay. But for more involved projects that has multi-objectives behavior, some of the limitations come into consideration when we set up the control rules. Under different conditions, under dry weather versus wet weather, maybe we don't want to open the valve under wet weather only, or maybe the maximum allowable release discharge rate is only implemented in wet weather, but not dry weather. That's a capability that cannot be provided in the EPA SWIM control rules editor. And because of that, and in-house, our product team has developed a Python-based simulator that taps into the EPA SWIM 5 engine. This Python-based simulator is based on source code provided by Open Water Analytics. And how it works really is to interrupt at each time step when we are running an EPA SWIM model, and at each time step, our RTC simulator will take in the water depth, the conditions of the site, how much runoff are we expecting, how much remaining storage volume is available, and any other restrictions that I may have covered just now. And then it spits back one thing only, and that thing is what's the percent open for the Opti valve. Say after all of that logic decision model, we decide to open the valve to 50%. So that is what spits back into the EPA SWIM 5 model. And at the next time step, all of this will happen again, and maybe the logic will tell it to close the valve entirely.
Ari has his hand up. Let's allow him to ask his question.
Sure, Ari. Ari, you're muted. Oh, okay. Ari accidentally clicked the hands up button. That's okay. We'll continue. So up to now, I've covered a lot on software configuration. So my colleague here, Rosa Santillan, will talk a little bit about the integration between software and hardware and how it looks like on site. So Rosa, I'll hand it over to you here.
Great, thank you so much, Kenneth. So as Kenneth mentioned, the software can only do so much without the hardware. Well, similarly, the hardware can only do so much without the software. So thank you for that explanation. Here on this slide here, I do want to bring your attention to the very different applications that Opti can manage. So we do have surface ponds. These could be wet or dry surface level ponds, as well as underground detention systems. And we do partner with third-party infrastructure manufacturers, whether those are chambers or more traditional concrete-based basins. The point is that we do have various applications, and every site is unique. So as we walk through this site, let's go ahead and do a click. You'll notice that the hardware, the certified program that we have here in Opti is a very rigorous program that, as we partner with third-party hardware providers, we vet these different components to a point where they are meeting the expectations, not just of the users, but also Opti and the integrity that they would provide for the overall system. So here, as we move through the slide, you'll notice that some of the components are very similar. Actually, they are the same essentially, and they can be applied to various situations. For example, on the right, you have an underground detention system where the control panel is mounted on the side of a building for more urban settings. On the left side, you have a solar system. We do offer line-powered and solar-powered systems, and you can see here that it's mounted just very out in the open there. You also have your outlet control structures, which again, these are on an at-need basis with your design. So we work with design engineers, we work with our partners to identify the type of outlet control structure that we are working to control. So again, you see they're different, but in a way they're still the same components. One more. You also have the spotlight of the show, if you would. You have your actuated valve assembly. Now for this, we do take into consideration, and we'll go more into detail about that in further slides, but we have the possibility of adjusting these within the certified hardware program. Again, we do have certain components, but they are adjustable to your site. So on the left here, the outlet control structure may be in an area where it allows for the protrusion of the actuator above ground for easy access. Whereas on the left, because again, this might be, I don't know, it could be a grassed area on top, or it could be a parking lot where the actuator has to be fully housed in that outlet control structure. So again, using our certified hardware, we can help you integrate your design and make it work for your site. Additional components, and these are true both for any application, is a pressure transducer. And this allows us to read the different levels of water. And as Kenneth was mentioning earlier, this is very important when it comes to the software configuration, as Kenneth and I both work with you through your design. When it comes to implementation, we want to make sure that we have the site calibrated in pressure transducers and other level sensors that we're currently working into our certified hardware program will allow us to have that near real-time experience with your site. And then here we have a steering wheel. There are some situations because of the fluctuation of water levels, or maybe it is in an area where there's a lot of movement. Maybe you have, I don't know, jet skis, for example, where the application will be. We do have steering wheels that allow us to have a very precise location for the water level sensor or pressure transducer. So again, that is applicable throughout every site, these two components. And then the next two components, which is a rain gauge, that is very unique to sites that require it. Maybe the facility may not be very close by to a rain gauge, so your project could facilitate the collection of data in that way. And finally, we have solar panels that are available for solar site system. If you are in a very rural area where there is very little to no power connections, or maybe the cost of the project does not allow for a power run, we do offer solar panel systems as well as systems with uninterrupted power supplied components to them. In here, I do want to bring your attention to current resources. While Kenneth and I are always here, and the rest of the Opti team is always here to help you and guide you through the project lifecycle, we do like to offer some self-guided tools that you may want to reference throughout your design process. So if you go to optirtc.com, we do have a partner resource page that allows you to download some of this reference information, such as a design overview guide. It also has a very good information on site selection if you're in those early stages, such as a feasibility assessment that we talked about in the previous session. We also offer specification and data sheets like the one you see on the right here. We offer PDFs and DWG files for CAD manipulation so that you can integrate them directly into your design set. And then we also have certified hardware details. The data sheets offer more in-depth data on how the hardware is manufactured, any warranty that is through the manufacturer. So we do provide a lot of that information just for your peace of mind. It is part of our user onboarding experience, and just to make you feel comfortable throughout the design process and as we moved into implementation and finally support. And then here, I do want to emphasize that we also provide, again, very specialized design guidance throughout the process, as well as best practices. On the left here, you have more mechanical type of best practices and guidance that we look with our design engineers, such as, again, every site is unique. So is your site, will it benefit more from electrical power runs, or do we want to integrate a solar power system? We look at outlet control structure retrofit in valve sizing through our configuration software, like Kenneth was just explaining. We also look at the best location for the hardware within a site and cellular connectivity. On the right-hand side, we have more design and cloud-based regulatory requirements that we also build into our design guidance and best practices. Safety requirements are a must here at Opti. We have fail-safe capabilities and various different types of alerts and alarms that come with the software. And then, of course, O&M, which is operations and maintenance, and accessibility. And as you can see here from the little graphic that I have here, there might be times where we want to utilize the entirety of the space and cater to that design. So again, we're looking at accessibility, safety from different points of views. And we can go more into detail in other webinars that are coming as we move through the project lifecycle. But for the time being, I just wanted to bring this to your attention and let you know that you're fully supported throughout the process from solution design all the way to the end. So with that, I'll give it back to Kenneth as he kind of walks us through some CMAC case studies.
Thank you, Rosa. So we looked at the processes through software configuration, and Rosa talked about the associated hardware components on site. So let's spend a couple minutes to look at a case study to really understand how this process worked better. This case study is based on an ongoing project with some small tweaks. We're keeping the name of the project private to respect our customers' privacy. And we also made some theoretical changes to make the webinar flow goes better. So the case study we're looking at here is in the Northeast region. The site is facing multiple challenges. There's water quality problems, downstream restrictions. We need to attenuate the peak flow. And it's also in an urban environment, so there is space limitation. We cannot really expand the storage volume at all. And I have highlighted some of the key metrics for the physical properties of the site. The adaptive control volume, that is the control volume between the valve invert and the overflow elevation. So the stage storage can be made beyond this elevation range, but what Opti can control is only within the adaptive control volume, because below the valve invert, we cannot discharge any water. It's standing water. And above the overflow weir, that is a passive design limitation. So unless we are raising that weir elevation, as such, raising that control volume, otherwise, this is the adaptive control volume that we can control. For this site, there's also a maximum discharge rate limitation limiting us at 0.82 CFS with an upstream tributary area of about 50 acres. And we also know that for this site is designed to capture up to a 1-inch event. Okay, so let's jump into selecting the behaviors. So to solve some of the water quality problems, we need to increase the detention time. So we need to employ post-event retention. And to reserve downstream conveyance capacity to maximize the storage available within this facility, we also need pre-event drawdown. So it's a multi-objective behavior configuration for this site. And the probability threshold is 60%, and the quantity, that is the volume, precipitation volume threshold, is set at 0.01. These are defaults for most of our sites. We usually implement these settings first and then gather more data to see if we need to make changes as we see fit once the site is implemented. And to start with, we look ahead for 24 hours into the weather forecast. And once the rain event has passed, we are closing the valve for an additional 12 hours. And then after that 12 hours, the stored volume is slowly released for over the next 12 hours. So within 24 hours after a rain event has passed, the stored volume should be released. And at the same time, we're considering that maximum control discharge rate of 0.8 CFS. You also notice there's a fail-safe behavior. So this tells the site what to do if there is an interruption in connectivity between the control panel and the cloud platform. For this site, we want to open the valve fully to avoid any local flooding, to revert the site back to a passive design configuration. We define the control logic, behaviors, and have configured the key parameters. And then we take all of these into a baseline configuration and run an H&H EPA SWIM model simulation. To start with, the yellow line here is telling us the target water level that CMAC is telling the site to maintain. And then this dark blue line is the actual water level within the facility. The light blue line is showing the elevations, what the pond elevations when it is raining. And you can see that on the top graph is showing over the next 24 hours. This is the amount of runoff volume the site is expecting. And this is the associated precipitation provided by weather forecast. You can see that we are able to draw down a pretty good amount, but we're not able to meet the target volume set by the system. And during the wet weather event, in this baseline configuration, the site is expected to overflow even for a 0.25 inch event. So for this event is 0.25 inch, and then there's an 18-hour dry period and a second event with a total precipitation volume of 0.75 inch. That totals up to be a 1 inch precipitation volume over about 2 days. And the same thing happens for the second event. Once the overflow occurs, the pond elevations start to decrease because the site is preparing for that second event. Is almost matching the target volume because this time we have more time to prepare. But still, towards the end, it still caused an overflow occurrence. So we looked into a couple changes in configurations, helping to increase performance of the site. What did we look at? We changed the maximum flow rate requirement to only apply during wet weather conditions. Talking to our customers, we think that during dry weather, this flow rate limitation is not a concern. And as such, we only have to, we only need to implement this restriction during wet weather. So overall, the results look a lot better. You no longer see the yellow line other than this tiny bit here. That's because the system is able to fully meet the target water elevation decided by the CMAC system. And there is no overflow occurrence throughout the 2-day consecutive rain events based on what is being shown from the EPA SWIM model simulations. And this is the new configuration that we are using for the existing site for the ongoing project. This is what it looks at the site. On the left, we have the site plan. The flow direction goes from left to right. There's a trash rack. This is an existing concrete structure, also shown on the graphic and the image on the right. And there's the opti valve. That's the opti valve. It's also shown in here in the site plan. There's a 12-inch butterfly valve controlled by the opti control panel box here. And this site is equipped with a solar kit. And our solar kit, solar powered control panel, can be implemented for valve size up to 24-inch. Anything bigger than a 24-inch, we probably need to connect to a line powered system. So that concludes our case study. And I also want to mention that at Opti, we understand there are many regulatory approvals, requirements at different states. Different states have different requirements. We always work with the local agency to try and evaluate how our system can help in terms of calculating credits, minimizing pollutant loadings, and other water quality challenges. And on this screen here, I'm showing this success stories of where regulatory approvals have been seen implementing Opti products. And we have over 300 deployments up to this point. And we're excited to work with you on future projects to implement Opti products and see how we can bring improvements to your existing or new projects. This is the end of the webinar today. Any questions, please feel free to bring them up now. Again, my name is Kenneth Yu. I'm a hydroinformatics engineer at Opti, and also my co-presenter today, Rosa Santillan. She is project manager at Opti. And thank you, everyone.
Thank you so much, Kenneth and Rosa. Very informative. I do have a couple of questions that have been coming in. First, as you had mentioned early on, a fail-safe mode, so that in the event of a system going offline, right, it goes into that fail-safe mode. How often do these sites go offline? And is that something to be concerned about?
Usually the site has a pretty good connectivity. It's largely based on the strength of cellular signal. For most sites, we're seeing 90% plus of connection time. And that's a continuous monitoring metric that we consider. For some limited occasions, we have seen challenges in cellular connectivity. One of the way to resolve it is to look for a stronger antenna, which can help to strengthen that cellular connectivity, and also maybe looking at additional service providers.
Great. Beth has her hand raised.
Hi, Kenneth. Are there any concerns about vulnerabilities in terms of cybersecurity?
Yes, we do. In fact, our product team has been talking about cybersecurity, and our cloud server is hosted on Microsoft Azure, which is our partner, and they take cybersecurity very serious concern. So that's something we actively monitor and have discussions with. And Victor, and feel free to chime in here. I know we are also thinking about other ideas which we may be able to communicate in a later time.
Yeah, and as part of the follow-up, we're happy to provide our security protocols that can be found on our website as well.
Okay, thank you.
Another one here is, can you talk a little bit more on the certified hardware program real quick? If we have our own hardware, can we use it?
Yes, and I can take that question, Kenneth. Yes, so for our certified hardware program, and we'll definitely go in more detail in the upcoming webinars on that. What we do is we have a very rigorous certified hardware program in which we have partnered with third-party integrators and hardware manufacturers. And this is again going for that safety and making sure that the objectives are met. If there is a particular project that is absolutely necessary, we can certainly look at that on a project by project basis. However, we do like to stick with the certified hardware that we have already put through months and months of testing to make sure that it matches up the objectives. And 9 times out of 10, we'll find something that we can integrate into your project. But if it's something that is absolutely necessary, we're more than happy to take a look at it. And if it's something that continues to surface, then we might bring it into our certified hardware program. Thank you for the question.
Priya, you have a question?
Yeah, I want to know how accurate are the sensors? What is the error rate?
What is the error rate
Yeah.
on your percent captures?
The error rate on what type of metric are you thinking, Priya?
These are about all the sensors.
Oh, for the hardware.
Yeah, for hardware.
Yes, we do have data sheets available, so I can certainly take down your information and we can look at that so that we can provide you a satisfying answer. And we can certainly go through the data sheets that we have for the certified sensors that we use with our systems, as they all vary slightly.
Yeah, and I have another question. So, like the internet connection is up 90% of the time. So, where is the data saved? Is it saved in the control panel for 10% of the times when there is no internet connectivity with the cloud?
It's a good
It is,
question. So
yeah, that's
if
a good question. It is
where's the data
communicated.
stored when the system is offline, right? Do we lose that data or is it stored locally?
It depends on the how long of a duration that we have lost the connectivity. If it's say over 15 minutes when the site entered fail-safe mode, we may lose some of that data, and we can always trace it back, try to have an educated guess on from the time series available in our database. But yeah, it really depends on how long that outage is lasted for.
And on that same, I do want to say that we are working diligently, and there are already sites that we have uninterrupted power supply. So if we do have very sensitive sites where we need that extra leverage above and beyond our fail-safe capabilities, we do offer that uninterrupted power supply as an external battery backup. So that will give you multiple days of continuous runtime so that we do not lose any of that data. So again, case by case scenario, but we do have that available.
Okay, so if there is limited storage there, so won't this decrease the life of hardware? So this is one of the aspect. Another aspect is because sometimes we write programs in such a way that it consumes memory. So won't there be any memory leak which will reduce the life of hardware?
Victor, do you want to talk in terms of the data leaks? Because I think that's a little bit separate in terms of the life of the hardware. We can certainly go into detail about that, but I think the concerns are more about the data and what happens to it, any data leak. So I'll defer that one to you, Victor. If you have an answer, we can follow up as well.
Yeah, that doesn't impact the life of the hardware. But again, as we mentioned, we are working on capturing more of that locally when we have offline periods.
Yeah, sure. Thanks. So actually, my question was about memory leak. Sometimes it is like if there is a program running which is continuously consuming memory without freeing the previous memory. So in these kind of cases, the life of hardware, maybe it should be 20 years, but it will live only for 5 years.
Interesting. Yeah, if you're available, we'd love to talk to you more about that online.
Yeah, sure. Thanks, Victor.
Excellent.
Those were my questions.
Thank you.
Thank you so much. Well, this has been a wonderful talk. I appreciate everyone hanging on till the end. We are out of time, so I'm going to have to wrap it up. I do see a couple of questions that we didn't get to, so we'll be sure to respond to you there. Some of those questions are on costs, and those are easier conversations to have in one-on-one. So with that, I'm going to thank you and encourage you to be on the lookout for our next webinar as we dive in a little bit deeper and get into some more details on these different topics. Thank you again and have a wonderful day.